So, welcome everyone. Now we are into the lecture of quantum mechanics, and this is our first lecture for this. And let me give you a brief about our syllabus. So, exact syllabus from UPSC notification is wave particle duality, then Schrodinger wave equation and expectation value, then uncertainty principle, then solutions of one-dimensional Schrodinger wave equation, and that too for free particle. Okay. Particle in a box, particle in a finite well, linear harmonic oscillator. Also, we are required to learn reflection and transmission by a step potential, by a rectangular barrier, particle in 3D box, density of states, free electron theory of the metals, and angular momentum. Apart from that, we are required to understand the hydrogen atom because that is very basic atom and that has led us to very important quantum mechanical phenomena, and then we are required to understand half spin particles, properties of Pauling spin matrices at first. Okay, so now let us move to history of quantum mechanics. So history of quantum mechanics really initially used to do that it connects the matter and radiation. One very good example is photoelectric effect, for which even the Nobel Prize has been announced. And then in quantum mechanics, we really do observe the phenomena at microscopic level. For example, we know Newton's laws of motion, that external force is actually rate of change of momentum or laws of inertia or the action of pendulum or whatever you may imagine. These all are the macroscopic phenomena. But what happens at atomic level and what happens at subatomic level? This is what we do talk in quantum mechanics. So the basic timeline, we may remember that classical mechanics is actually started by Newton, Hamilton, and Lagrange. Now, for the electromagnetic theory, we know that Maxwell and Hertz have done well. But for quantum mechanics, let me tell you that it has uh, Max Planck, Einstein, Compton, Niels Bohr, Louis de Broglie. So look, this is not Broglie, but this is pronounced as de Broglie. De Broglie. Okay, so this is its pronunciation, the correct pronunciation. Now, Davison and Germer, who confirmed the very important part, Heisenberg, and many more. These are the Nobel Awards which you may know for your general knowledge and for your interview purpose as well, because we are required to know it as we are also the UPSC aspirant, not only the student of physics. Now, we are going to start from introductory quantum mechanics. That means we will get introduced towards quantum mechanics, and that is we are doing it through actually by studying black body radiation. Black body radiation. Why we are studying the black body radiation? Because matter and waves are connected, and it is evident in this radiation. Matter and waves are connected. And we will also study its introduction and broader aspect only. Introduction and broader aspect. Why? The reason is we will again look into it at uh, look into it when we are in thermal physics. Okay, so it is also in thermal physics, so we are required to study. So black body radiation is important. The reason I have stated, because it connects matter and waves. How? Let us see. So black body radiation is actually touted to be the theory which actually started to explain the origin of quantum theory. So The origin actually lies in explanation of black body. How? So let us know what is ideal black body at first. So ideal black body is anything which is absorbing all the radiation you are throwing on it. That means whatever you throw at it, it absorbs all, and that is why it is named black body, because nothing is being reflected or re-emitted. Okay, and we know that all the objects either they emit something, absorb something, and reflect something of the radiation, है ना? And all the objects actually do these all things in some kind of combination. Now, let us start to know that an ideal black body does not exist actually, but we are knowing it in theoretical fashion only. Although we are required to know what is its nearest approximation. So, nearest approximation of ideal black body is a hollow enclosure with black inner walls. That means they are going to absorb the most part of the radiation, and a small hole as an entrance for radiation. So from where the radiation may come. So here the radiation is coming, and after successive reflections, they are finally absorbed with inside the hollow enclosure only. And as all of the incident radiation is actually absorbed, that means it is a black body. Now let us know that Herd's experiment also proved that light is an EM wave. Okay, and it also follows from the Maxwell's law of EM wave. Look, Maxwell in electrodynamics already has proved that what is light, and these all things they all are EM waves. And this is actually a very interesting case where in someday I may post something. Okay, so how does the nature complement each other? How does the different aspects of nature do complement each other? We will know it from that special story. But right now, for our theory part, it is fine. Now, let us look at the origin of EM wave. Okay, so remember how hot objects glow. You see this picture. Okay, in this picture, the iron rod is heated actually, and because of the so much heat, it has gained some kind of energy, and that energy is being re-emitted in form of a glow, a kind of radiation. So as temperature rises, it glows. As temperature rises, it glows from red to yellow to white. Different kind of they will actually radiate out, radiate out different wavelengths at different temperature. That is why the color of the glow is changing. Okay. Now, let me tell you, such a glow is associated with the most fundamental property of object to absorb, because it is absorbing some kind of radiation and then only it is getting in excited state and then it is re-emitting that. Okay, and let me tell you the broader explanation you will get in thermal physics in the chapter thermal radiation. Now let us move back to black body, and if the enclosure is heated to a certain temperature T, it emits radiation in that temperature's accordance. Now wavelength-wise distribution of emitted radiation of black body is observed slightly bizarre. So there were a different theoretical explanation and the different experimental observation. So theory was different and in the initial phase, and the experiment's result was different, and that too the wavelength distribution as per the uh, temperature and the corresponding intensity as per the wavelength. Okay, so it is saying that it is found that energy radiated out from black body upon heating is maximum at a particular wavelength lambda m. Okay, at a particular wavelength, say the wavelength is lambda m, for maximum the radiation is maximum, that is energy of the radiation is maximum, and for is very small for very short and very long wavelength. Okay, so you can see that the intensity is small here, the intensity is small here, but at certain value of wavelength it is maximum. So why such a bizarre observance of the experiment? So to explain this only, This was such a huge thing at that time that many scientists tried to explain. Okay, so to explain this only, many scientists came forward. They put forward their explanation, and we know them in the form of Wien's law, okay, Planck's law, and things like that. So various attempts were made to explain such a pattern of radiation, and one such attempt was actually the Wien's law. Wien's law says that the intensity, which depends on wavelength and temperature, is actually some constant multiplied by exponential minus b upon lambda t divided by lambda to the power 5, and a and b are some constant. This law was fit for shape except long wavelength. So this law was fine till here when the wavelength was short. But as the wavelength is increasing, okay, as the wavelength is increasing, this law was not fit. So we need some formula which correctly explains this one. So this is the observed intensity, and that is why we are trying to make a formula which is actually fit for it. And how those formula arrive right now in this introduction to quantum mechanics, that is not required. We are only required to know whole story. So know that what will happen at thermal equilibrium. So at thermal equilibrium, energy density of the radiation inside the cavity will be equal to energy density of the atomic oscillator in walls of the cavity. So what is assumed that in the walls of the cavity, the energy is being absorbed by atoms, and once the atoms are actually absorbing the energy, they are oscillating. So it is kind of oscillator. So that was the new theory. So now you can show that the number of oscillators per unit volume of frequency nu is given by Jeans number. So what is the number of oscillator? Like how many such oscillators are there? Okay, and that to oscillator at a certain frequency. If you change the frequency of the incident radiation, the things will change. So it is given by 8 pi nu square divided by c cube. Okay, and again let me tell you, here you are only required to know the basic formula, note the whole concept. For the whole concept, you will read the same thing in thermal radiation chapter. Now applying the equipartition of energy, which says that per degree of freedom, the average energy is kT. So here we have applied the equipartition of energy, and this is what we are required to write in answers as well. You are required to write what you are actually doing. So you are applying the equipartition of energy to this. So what will happen? Per degree of freedom per particle, we have kT energy, and there are n such particles. So what you will do? You will find the energy density of radiation of frequency nu and temperature T, which is given by this value U, which is function of frequency and temperature. And number of such oscillator is now multiplied with the average energy. Average energy is kT, and number of such oscillator is n times nu. And now we are simply multiplying, and this whole thing is called actually Rayleigh-Jeans law. Okay, so you must focus on the color code. I am using a different color of highlighter to make it very clear to you all. And when you change this equation in the wavelength form, like you can always convert the frequency into wavelength, because frequency is upon c upon lambda. C is the speed of light, because light is also EM wave. Okay, so we use this and we got this, okay, in the wavelength form. So we could notice that this intensity is actually proportional to this energy density, okay, and the exact relation to such intensity is actually given by this formula, Cy4 multiplied by the energy density of the radiation at frequency nu. Okay, this is the main thing here. So hence, let me tell you that Rayleigh-Jeans law is found to be good for long wavelength, okay, but for shorter wavelength it is again failing, it is diverging. This problem is called actually ultraviolet catastrophe, and it is actually previous year question of our UPSC. Okay, so you must know what they are asking in previous year question paper, because if you know what they are asking and from where they are asking, you will be able to understand it yourself as well. So to understand ultraviolet catastrophe in broader manner, you may consult UV catastrophe. For this part, you may consult Modern Physics by Arthur Weger Shobhit Mahajan. By Arthur Weger Shobhit Mahajan. Okay. So in that, they have explained ultraviolet catastrophe in very brief manner. Now, let us focus further. So, if we integrate this value over all the frequency range, we will actually get the energy. And when you are doing that, you are getting infinite energy. Okay, when you are solving this equation, you are getting infinite energy. And this U nu is actually given by here, which we have found. Okay, it is Rayleigh-Jeans law. So energy density is being integrated over all the frequency range from 0 to infinity. Okay, this is 0 and infinity. And when you are doing it, you are getting infinite energy. So now we all are smart enough. We will know that how could the infinite energy be existing. Okay, so whole correction is required. And now the real correction was done by Planck. And they actually used the Maxwell-Boltzmann law. They used MB statistics. You will know it in thermal physics very well. Okay, so they use this statistics to prove these points. And now the energy density is given by this very beautiful formula. Okay, where you are required to memorize it by your heart. Let me recite the formula for you. It is again the function of frequency and time. And whatever is the function of frequency and time, that may also be written as the function of wavelength and time, because frequency and wavelength are related directly by nothing except one constant, that is speed of light. So it will be very, very easy. So it is 8 pi frequency square divided by c cube. Now h nu divided by exponential h nu upon kt. K is where Boltzmann constant. Okay, -1. And in below we have written it in the format of wavelength and temperature. So what is the special mention? Like UPSC may ask you something briefly. So I have written it briefly in your own language in the real examination UPSC. If they are going to ask you, we may write it. So a special mention. What is a special mention about Planck's law? Okay, it is hot topic for UPSC. Let me tell you. So there should be a special focus. So as temperature is increasing, Planck law is becoming Wien's law. Okay, we know Wien's law very, very clearly from here. This is what where we do have Wien's law. Okay, so this is Wien's law. They it is fit for the this or observed shape except long wavelength. So we have written as the wavelength is reaching 0. But if the wavelength is reaching infinity, then it becomes Rayleigh-Jeans law. Okay, this is mathematically verifiable. You just make the wavelength tend to 0 and see yourself what happens. But for the examination purpose, we are required to be smart, and smartness means learning and memorizing as well. Learning plus rote memory power is required, because you cannot understand and learn each and everything. So I will always tell you that what to study and what to memorize. So till now, these all were the process. Okay, these all were the process which we are required to study, but these are the two very big results which we are required to remember. These again are very well-defined process which we are trying to memorize. Okay, now it is consistent with Wien's displacement law and Stephan law. Okay, where the energy density is actually proportional to fourth power of temperature. So look, this T is temperature. Now we come to know that it diverges means what different kind of thing. So look, we know that the Planck law is now the correct thing. So here we can see this is the Planck law. Okay, and this blue line is Planck law. Okay, so look, the Wien's law in this region, it is agreeing to the Planck's law, that is the observed experimental result. But Rayleigh-Jeans law, okay, this Rayleigh-Jeans law is totally different for the larger wavelength. Okay, and this is what I have given. This is what we used to call the ultraviolet catastrophe as well. Okay, here we have written it, ultraviolet catastrophe, which is actually the divergence of the Rayleigh-Jeans law for shorter wavelength. And this is our previous year question. I have just reminded you once again. So this is what we were to be introduced in black body radiation. Okay, now let us solve an exemplar problem. So problem is that we are required to show that Planck's law reduces to Wien's law in short wavelength limit and Rayleigh-Jeans law if the wavelength limit is long. Okay, for short wavelength it is Rayleigh-Jeans law, and for long it is for short it is Wien's law, and for long it is Rayleigh-Jeans law. So we are required to prove it. We have just written it here as well. A special mention. This special mention is very important. It is very important. You must memorize it at any cost. Now, so Planck's radiation law is actually given by this. Okay, and let me tell you, Planck's radiation law is what is getting validated with experimental observation. Validated the experimental observation. So now when lambda is small, so this exponential term will be a way larger than 1 because lambda is in denominator. Okay, so therefore the value would be this. Okay, it is mathematically done, which is obviously the format of Wien's law, because if you know Wien's law, it is simply that intensity in the form of lambda and T is actually some constant A, and then we must look it at some constant A divided by wavelength to the power 5 exponential minus B divided by lambda T. Okay, so this is what, this is lambda to the power 5, and this is what, minus some constant divided by lambda T. Okay, so this is actually the Wien's law which we have proved. And now when wavelength is large, Vm approximate for the large exponential hc upon lambda kt, it is going to be 1 by hc upon lambda kt. Okay, that is what we call approximation, and we must learn it from mathematical physics. But now just remember it. And again, I am sorry if you are getting some kind of outside noise. My room is right now not totally isolated, but we must continue our learning, so we will neglect some noises and we will focus only on signal. That's our motivation. Now, when you apply this in our Planck's formula, you will actually get this, which is nothing but the Rayleigh-Jeans law. So this is what I have guided you in the broader. Now you must know that how does the mathematics happen, because in physics, nobody is going to teach you mathematics at such a level. So mathematical physics should always be very, very clear to you that how the exponentials are being expanded when something is being large, when something is being small. Okay, and we are done with this problem. Now we want to study photoelectric effect, which I am leaving for the next lecture. So let us meet in the next class.